morning. Today we're going to start our discussion of Chapter 13. So we've spent the last two chapters talking about the three fundamental phases of matter, right? We talked about gases in Chapter 11, and we talked about liquids and solids in Chapter 12. Well, in this chapter, we're going to talk about another very common form of matter. It's not an actual phase, but we actually see it quite more often than we do with actual pure phases of matter, and these are what we call solutions. Now, we've talked about a solution before, we just didn't call it a solution. Very early on in the semester, we talked about homogeneous mixtures, which were just simply a mixture of two or more substances combined with a uniform composition, right? A solution is just another name for a homogeneous mixture. And solutions, in fact, are the most common form of matter that we find. Many things that we encounter on a daily basis are actually solutions, even though we may think that they're in one material because they look like one material, being homogeneous. So a few examples of this are, say, something like ocean water or even tap water, right, which contain all sorts of different materials dissolved in them. Your blood is another example. Blood plasma is a solution of several materials dissolved within your blood. So lots of things are actual solutions. We just don't think about it that way. And we'll mention a few more examples as we go through. So again, a solution is just simply another term for a homogeneous mixture. Now, solutions can come in different forms, where our two parts of solution, which we'll define in a second, are what we call the solute. Right? The solute is what is dissolved into something. So this is what we commonly refer to as the minor components. And the solvent, right, which is the major component. And whatever the phase of the solvent is, that'll be the phase that the solution takes on. So this can come in different forms. So for example, we can have what are called gaseous solutions, where the solvent and the solute are both in the gas phase. Now, the most common example here would be air, right? What we breathe, right? It is not, of course, a one material. It is a mixture of primarily oxygen gas and nitrogen gas with some other gases dissolved in there. Now, in this particular case, right, since the major component of air is nitrogen, nitrogen would be the solvent of the air, and the other gases, including oxygen, would be solutes. Now, we can also have solutions that take on the liquid phase, so meaning their solvents are going to be liquids. And these can come in three different forms, right? They can come where the material that we're dissolving, the solute, is either a gas, a liquid, or a solid. So, for example, we can have carbonated water, right, where we're dissolving a gas, carbon dioxide, into the liquid water. We can have things like ethanol and gasoline, or ethanol and water, which gives us all of the different alcohols that we drink. We have two liquids mixed together. And then we can have solids dissolved in liquid, of course. For example, seawater, where we have things like sodium chloride and other ionic compounds dissolved in the water, or sugar in water, another common example here. So these are the most common forms of solutions. Now, there is one other type here that we'll mention, and this is what we call a solid solution. But we have to be a little bit careful when we think about a solid solution, in the sense that how these materials are actually combined. So in a solid solution, both the major component, the solvent, will be a solid, and also the solute will be a solid. Now, the thing that we have to remember is that you cannot mix the materials as solids. So for example, You can't take salt and sand and mix them together in their solid form and get a homogeneous mixture, get a solution, right? Even with grinding, etc. The way that you have to do it is you have to melt the solids and then mix. And this is how we make all of the metal alloys that we think of. Some old ones are things like brass and bronze, and there's a lot more modern alloys that we use in the construction of a lot of different things, like alloy wheels and alloy parts for cars and airplanes, etc., where they're actual mixtures of different metals, right? And to create those, the metals are melted and they're mixed as liquids, and then those liquids are allowed to resolidify, and that new solid is a homogeneous combination of the two materials that were mixed together. And so solutions can take all of these forms. We will in this chapter focus on the gaseous and the liquid solutions, and we'll focus on solutions that have a solvent that, of water. Now, let's define some of these terms that we've been talking about. And so first of all, we mentioned that a solution has at least two components. We have the majority component, which is called the solvent, and we have the minority component or components, which is the solute, right? There can be multiple solutes, but only one solvent. And again, the phase of the solution itself is going to follow the phase of the solvent. Now, if we have a liquid, if we have a solution where the solvent is water, then we have a special name for that, which we've heard before, and these are what we call aqueous solutions, right? So when we've been talking about chemical reactions, right, we often talk about materials dissolved in water, right? And we gave them a special symbol, AQ, after that material within the reaction. And this is because they are what we refer to as aqueous solutions. So whatever the material is, it has been dissolved into water to create a solution. Now, what kind of solvent do we choose, right? Well, why does a certain solvent work for certain things and not for others? Well, the first thing I'd like to remind you of is back in chapter 10, right, when we talked about polarity, we mentioned this idea that oil and water don't mix, right? And we explained that in the fact that polar materials like to mix with other polar materials, and non-polar materials like to mix with other non-polar materials. And this is what we follow when we try to make up solutions. We follow the saying that like dissolves like, meaning if we have a polar solute, then we're likely to want to use a polar solvent to dissolve it. The most common polar solvent is going to be water. Now, there are other polar solvents like alcohols, like ethanol and methanol, or acetone, which I think you've probably all heard of. But if we want to dissolve something like oil or other non-polar materials, we need to use a non-polar solvent to do that. Something like hexane or toluene or various other non-polar materials. And so when we go to clean up an oil spill, right, on our garage floor or something, we don't try to clean it up with water. We either have to put soap in that water, as we talked about in chapter 10, how the soap allows the non-polar materials to dissolve in the polar solvent, or we need to use a non-polar solvent, like hexane, or what you might find in the store as something like mineral spirits or paint thinner. These are different forms of non-polar solvents. So now I want to turn our attention to the actual formation of these solids. So we've talked about kind of what they are. I want to talk about what's involved in making them, if we think about it at a molecular level. So the first thing that we can look at is what are the interactions that are going on within a material. So in the previous chapters, we've referred to things called intermolecular forces that hold atoms and molecules together in our materials. Right? And so when we have our pure materials, so when we have our solvent, they are interacting with each other by what we'll call solvent-solvent interactions. This is going to be some type of intermolecular force. And the solute, whatever that might be, is being held together by some sort of interaction. So that could be some type of intermolecular force. It could be an ionic bond if we're talking about dissolving an ionic material, or it could be something like a dipole-dipole interaction if we're talking about things like sugar molecules. So it's going to be some sort of interaction holding the solute molecules to each other. So these are the interactions that we need to break down when we go to dissolve them. Because in order to mix these things homogeneously, we have to separate them to allow them to combine. So during the process, we're going to be breaking down the solvent-solvent and solute-solute interactions, but the key is we're going to trade by forming new solvent-solute attractions. And this really is what allows a solution to form, is that while we might be breaking apart some relatively strong interactions, we're going to be forming new interactions that are equally as strong or maybe even stronger when we make a solution. Now, if these new interactions are weak, then the solution will likely not form, and we'll get some things that don't dissolve in one another, like oil and water, right? Where we're going to trade strong interactions for weak interactions, and so it doesn't occur. Now, if we break this down a little bit further and look at how a solid dissolves in water. So when that ionic material, and we're going to use an ionic material dissolving in water as sort of our prototypical example. If we sort of analyze this, we have our solid, and our solid's going to exist as a crystal structure here. And remember, this crystal structure is being held together by ionic bonds. Now, these ionic bonds are relatively strong, right? They don't break down very easily, right? And we even talked about in the last chapter that an ionic solid like sodium chloride has a very high melting point, 800-900 degrees, because the sodium and chloride bonds are so strong, and it takes a lot of energy to break them. But we also see that something like sodium chloride very easily dissolves in water. Now, why is that possible? Well, the key is when you're melting something, you're not creating any new forces, right? You're just trying to break them down. But remember, when we're making a solution, we're going to replace those ionic bonds with new interactions with the solvent. And so, while this breaks down to give you the chloride ions and the sodium ions in solution, those ions form what we referred to in the last chapter as ion dipole forces, right? Remember, these are the special kind of intermolecular forces that take place when we dissolve an ionic compound in a polar solvent like water, right? And these ion dipole forces are fairly strong, and if you see here, we can form many of these forces with each ion. And so the ability to form all of these interactions allows the ionic solid to dissolve because we don't really lose all that much in terms of the strength of our interactions, right? We're trading these ionic bonds for these new ion dipole forces, and so energetically, it's favorable for this to dissolve, where it's not terribly favorable for it to melt because there's no new interactions being formed. So all we're doing is taking energy as opposed to giving off energy when we create these new interactions. So this is generally, right, if we think about it on a molecular level, how a solid, especially an ionic solid, right, dissolves in water, right? And so all solids, right, when they dissolve, they're going to break down, you're going to break their solvent-solvent interactions and your solute-solute interactions, and you're going to form these new solvent-solute interactions. And so the basic take-home here and the big picture is that when we dissolve an ionic compound, right, we exist as individual ions in solution, right? So when we think about that salt water, we think about the sodium chloride existing as sodium ions and chloride ions. Now, if we were to dissolve something like sugar, right, a molecular solid. Now, remember, when we dissolve the sugar, it's going to exist as individual or small groups of sugar molecules, right? It doesn't break down into ions. Right? But the key is we're going to break down into small groups of those sugar molecules, so it appears to disappear, right? So we're breaking down some of those intermolecular forces so that the water and the sugar can intermix, and as you get smaller and smaller groupings of sugar molecules, they become invisible, right? We don't see them anymore, and that's when we have our dissolved solid in our water. So again, now that we've sort of seen the overall picture, let's sort of put some vocabulary with it. So when we use the term solubility, right, we throw that sort of word around. We say that this is the solubility of this and this is that. Well, solubility is defined technically, right, as the amount of a compound, usually in grams, that dissolves in a certain amount of liquid, our solvent. Right? And so, for example, we could quote the solubility of sodium chloride, right, at 25 degrees as 36 grams of sodium chloride per 100 grams of water. And that would be the solubility of sodium chloride in water. Now, when we talk about solutions, we're going to talk about them in sort of its three different types, right? And on a sort of very qualitative level. We can have what we call a saturated solution, which just simply means you've dissolved up to the solubility limit. So for sodium chloride, that would mean we would have dissolved 36 grams of sodium chloride in every 100 grams of water. So a saturated solution holds the maximum amount of solute under those conditions, and any additional solute that we add would not dissolve. Now, we can also have, and this is probably the most common situation, we can have an unsaturated solution where we've dissolved less than our solubility maximum, right? So we're below a saturated solution. So we have less than whatever that solubility is dissolved. And if we add some more, then it will continue to dissolve until we reach that saturation point. Now, the third type, and this is the least common, right? This is what we call a supersaturated solution. And this is a solution where we've managed to dissolve more than what that solubility limit. So we're above that saturated solution. Now, normally this wouldn't happen, but we can make it happen. So if we think about sugar, for example. Now, one of the things that we'll talk about a little later in the chapter is that the solubility depends on temperature. So as we raise the temperature, a solid will become more soluble. So typically, one way that we can create a supersaturated solution is to dissolve the solute at high temperature and let it cool down slowly. And for some materials, that extra solid, the extra solute that's dissolved will stay in solution, and you will have what would be referred to as a supersaturated solution, because at your new temperature, you will have more dissolved than what you should be able to dissolve if you were just dissolving it at that temperature. Now, for most materials, once you get down to a certain temperature, that extra material, that extra solute will precipitate out, like we saw with precipitation reactions, right? Where you've exceeded that solubility maximum. So, solubility. Now, if we remember back to chapter 7, we saw a set of solubility rules. We had a set of rules where we could look at an ionic compound and we could say, oh, because it contains these ions, it's going to be soluble in water, or not soluble. Right? So this gave us a way to qualitatively describe the solubility, whether it dissolves or not. It's insoluble or soluble. Now, we're going to expand upon that in this chapter and continue to talk about that. Now, we don't have rules for molecular solids, right? For ionic solids, we have these rules, and now we can know that we can actually put numbers to that. We can have a quantitative description, and that's what we refer to as the solubility. But for molecular solids, we don't have rules. So we sort of have to do this by trial and error. Right? We have to use guidelines, and this is where things like dissolves like becomes important, right? Understanding that, table sugar is polar, so it's likely going to be soluble in a polar solvent like water, but maybe not soluble in a nonpolar solvent. Or that nonpolar solids like lard or vegetable shortening, right? These are not going to be very soluble in something like water that's a very polar material. So we have to use these guidelines to help us predict whether molecular solids will dissolve, since we don't have a set of rules that will allow us to do that. At this point, I also want to remind you of a couple of other terms that we referred to back in Chapter 7, again, when we did the solubility rules, to describe solutions. And this is, we describe them as an electrolyte solution or a non-electrolyte solution. And remember, the distinction here is that an electrolyte solution contains dissolved ions, so principally this means that we've dissolved an ionic compound, and therefore will conduct electricity, whereas a non-electrolyte solution will contain dissolved molecules, neutral particles, so something like we're dissolving sugar in water, right? And these will not conduct electricity. So we have electrolyte, which will conduct electricity, and non-electrolyte, which does not conduct electricity. Now, at this point, I want to talk about how the solubility varies with temperature. So if we look at the graph here, what I want to point out is just the general trend, right? We're not going to try to do, quantitative predictions here. Now, we can read graphs, and you might be expected to look at a graph and predict things, but in terms of actually getting into calculations, we're not going to do that here. But what I want to point out is, generally speaking, when we dissolve a solid, the solubility will increase with increasing temperature. Again, this is what I was referring to when we talked about making the supersaturated solution. So if we just take a curve, for example, we notice that they have different shapes, right? Some of them have very steep, so the solubility goes way up with temperature. Other ones are pretty flat. They go up, but very slowly. So if we just take two ionic compounds, which are on this graph, and we look at them, we can compare something like potassium nitrate, which dramatically increases, right? At, say, 20 degrees or around room temperature, it has a solubility of 30 grams per 100 grams. But at 50 degrees, right, just a little bit higher, right, that solubility has gone all the way up to almost 90 grams. So a very rapid increase. But for something like sodium chloride, right? At that same 20 degrees, the solubility is a little bit the same. It's pretty close, maybe a little bit above 30 grams. But if we go to 50 degrees, that solubility has only gone up to about 37, right? So it's just gone up by a few grams. And even up to 100 degrees, that solubility is only up to about 40 grams per 100. So while generally speaking, we can say that the solubility goes up with temperature, it doesn't always go up by the same amounts, right? The trend is a little bit different. Now, again, we can take advantage of this to do certain things, like I said, like create supersaturated solutions. Now, we're going to use an example here of a molecular solid to kind of talk about a couple of different things. So first of all, I don't have it written here, but if we want to create a supersaturated sugar solution, such as you might have in what we call sweet tea, right? Sweet tea is just very sweet iced tea, but the only way that that can be created is by using this temperature effect. So if we heat up the water and dissolve the sugar, we're going to be able to dissolve a lot more of that sugar. And then if we allow that sweetened hot water, hot tea, to slowly cool down, most of that sugar will stay in solution. And you might see a little bit, and you'll get a little bit of sugar plating out in the bottom, but most of that sugar will stay dissolved. And once it gets back to room temperature or even a little colder, right, you'll have a much sweeter version of that iced tea than you could ever create if you just were to try to dissolve sugar in iced tea, right? Even room temperature tea, right? You're going to have difficulty getting that much sugar to dissolve because the solubility is so much lower. So that's one of the ways that we can play with this. Now, another thing that we can do is something called recrystallization, which is a fairly common purification tool in chemistry. We can use it here to sort of illustrate this idea that if you were to, again, dissolve this excess sugar into water at high temperature and then allow it to cool down, and we get it to cool down even more, that sugar will eventually start to crystallize out, especially if we disturb it or we give it some place to crystallize, like a string or a stick, or we put small crystals in there. We can prompt or we can accelerate this recrystallization process, and it'll start to crystallize out on the string, and this is how we get these rock crystals, or what's sometimes called rock candy, by recrystallizing that sugar out of water. And that sugar will be pure, right? It'll be maybe even purer than the sugar that we dissolved if there was any impurities in there. Now, I want to turn my attention now to dissolving gases, right? So we've talked about dissolving solids, and again, the big thing there is, in terms of trends, is that as we raise the temperature, the solubility of the solid goes up. Now, with gases, we're going to see some different trends. So just remember, one of our common types of solutions, right, for a gas in a liquid is carbonated water. And this is kind of what we're going to use as our example. Now, almost all liquids that are in the air have dissolved gases. Now, gases don't have very high solubilities, right? We talked about how gases don't like to really dissolve. They have a large amount of kinetic energy. They're moving. They don't dissolve very readily, right? Especially in water. But they do dissolve somewhat. Now, we know this because, for example, fish can live in the water, right? They extract oxygen from that water. It's necessary for the fish and the other aquatic animals and plants to survive. So clearly, there are dissolved gases like oxygen and nitrogen in the water, as well as in other liquids like our blood contains blood gases, right? Nitrogen, oxygen, carbon dioxide, right? And so forth. So clearly, we have gases dissolved in our liquids, right? So these are all technically solutions, even if we don't add any, say, solids to them, because we have these dissolved gases. Now, if we look at the temperature, what I want to stress here is we have exactly the opposite effect as we see with solids. So while the solubility of a solid goes up with temperature, the solubility of a gas goes down with temperature. Right? So if we start to heat water, right, just tap water, the first thing you might notice is very tiny bubbles start to bubble up from the bottom of the solution. Right? This is the gases bubbling out, right? Because remember, as we heat up, those gases are going to get more kinetic energy. And remember, they have very weak intermolecular forces with the liquid that they're dissolved in, right? With each other. They form very weak intermolecular forces in general. And so it's really easy once those gases get a little bit of extra kinetic energy to just escape from the solution. And this is what we see with those tiny bubbles. And this is well before we reach the boiling point. So this is not boiling, right? These are the degassing of the water. And this would be things like nitrogen and oxygen, etc. So as we raise the temperature, that solubility decreases. So at room temperature, there'll be a certain amount of oxygen and nitrogen there. As we heat it up, there'll be a much smaller amount of nitrogen and oxygen there. Now, just to sort of make sure we understand the difference, when boiling occurs, those much larger bubbles, right, those contain vaporized water vapor, right, because that's when we're starting to get that internal evaporation. So water is vaporizing, and so we're getting water vapor or steam bubbles, not dissolved air, right? All the air, all the nitrogen, oxygen that was going to bubble out would have already bubbled out by the time we got to the boiling point. So another way we can demonstrate this, all right, is simply to take a hot liquid and a warm liquid and a cold liquid and compare them. So if you take cold soda, for example, and you pour it, which is going to agitate it, and so agitating is, one way we can sort of prompt more gas to come out of solution. What we see is that very little bubbling, all right, when we pour it cold. Because at that lower temperature, the gas has a higher solubility, and so it's likely to stay in solution. But if you have warm soda and you pour it, right, you may have noticed that it fizzes a lot, right? You get a big foamy, head on top, right? Because a little bit of agitation will cause that gas to come out because it has a much lower solubility at that higher temperature. And so just a little bit of shaking or agitation like this will cause that gas to rapidly come out of solution. Now, that's the temperature effect. Now, when we deal with gases, of course, we have to deal with pressure, right? When we talked about gases back in chapter 11, this property of pressure. And so the solubility of a gas is also going to depend on the pressure above the liquid, what we called the vapor pressure. Right? So the pressure of that gas above the liquid. And so if we look at this first picture, right, we're going to have always a balance between some gas dissolved in the liquid and gas above it. Right? Now, as we increase the pressure of this gas above it, so if we think about going to here, and so we put more gas above the liquid, what we're essentially going to do is we're going to force more gas to dissolve by sort of pushing it into solution, if you will, right? By putting more gas here, it's going to collide with the surface more, and we're going to get more gas to dissolve by putting a higher pressure of gas above the liquid or increasing the vapor pressure above the liquid. So this obeys something called Henry's law, which essentially says higher pressure equals higher solubility. So, to review, gases, higher solubility at lower temperature, right? So as you increase the temperature, solubility goes down, and higher solubility at higher vapor pressures or higher pressures of gases above the solution. So one way, easy way we can visualize this, again, is with our carbonated beverage. And when that beverage is packaged, when you buy it from the store, if you try to squeeze the can, what you notice is it's rigid, right? That is because it's packaged under a high pressure of CO2, maybe 3 to 4 atmospheres of pressure. And so essentially what we've done is we've forced a lot of CO2 to dissolve into that carbonated beverage, right? Now, as soon as you open that, what you see is a rapid release of carbon dioxide, that fizz, right, that occurs. And that is because now, instead of that pressure above there being 3 to 4 atmospheres, now that pressure is just atmospheric pressure, or approximately 1 atm. So at that lower pressure, now the solubility here is much lower. Right? And so all of this extra gas wants now to start to bubble out, and you get this sort of rapid bubbling initially, and then, of course, if you let this sit, it will continue to bubble out until it reaches the normal amount of CO2 that would be able to dissolve at 1 atmosphere of pressure above the liquid, right? At that point, once you reach that, you would have what we call flat, right? That would have the normal amount of CO2 dissolved that you would expect under these conditions. All right, so that brings to an end what I want to talk about in today's presentation. So next time we will talk about measuring the amount of solute that is dissolved, what we call the concentration of the material.